Alright, so we're going to go ahead and look at the equations of sinusoidal functions. So the standard equation looks like these two forms here. So y equals a sine b x minus c plus t, and y equals a cosine b x minus c plus t. Okay? So an example of a sinusoidal function might be y equals 3 times the sine of 2 x minus 9t plus 4. Okay? So you'll need a graphing calculator as you work through this exercise. I recommend Desmos graphing calculator. It's free and it's online. Just make sure you're in the right mode, whether it's degrees or radians. We're going to use mostly degrees for these examples. So what you'll have to do actually is to change the mode to degrees. You'll have to click the wrench that's in the top right corner. Everything I'm about to talk about applies to both sine and cosine functions. However, I'm going to mainly use sine functions just to be consistent. So what I want you to do now is open your graphing calculator, Desmos, or whatever you use, and graph these three functions. Pause the video, come back and see what you notice. Okay, so hopefully what you notice is that when you graphed y equals sine x, it looked something like this. So it alternated between -1 and 1, as you probably know by now. When you graph y equals 2 sine x, what you hopefully saw was that instead of alternating between -1 and 1, it alternated between -2 and 2. And y equals 3 sine x alternated between -3 and 3. Okay? So what we can really see is that the distance from the midline to the maximum here was 1. The distance from the midline to the maximum here was 2. And the distance from the midline to the maximum here is 3. So what's happening is that this number here that's in front is affecting the distance from the midline to the maximum. Well, the term for the distance from the midline to the maximum was the amplitude. So this tells me that here the amplitude is 1, here the amplitude, I should write amplitude is 2, and here the amplitude is 3. So what I can say is that A is directly equal to the amplitude of the function. Okay? Alright, so moving on to B now. So let's see what B does. So what I want you to do first of all is to graph these 4 functions. Pause the video, come back. Okay, so y equals sine x. When you graph that, what you hopefully would have noticed is something that looks like that. And the main thing I want you to see is that this x-intercept right here is at 0, 0. This one over here is at 360, 0. I think what you'll notice is as you graphed these here, this point right here moved further and further to the left, essentially just squishing the function so that one cycle happens a bit quicker. Alright, so if 360 is here, sine 4x might have one cycle being here. Okay? So what I want you to do is just read the period of each of these functions. Okay? So look at your graph. When my b value here is 1, you notice my period is 360 degrees. When my b value is 2, hopefully what you see is that actually this point right here occurs at 180 degrees instead of 360 degrees. So that tells me that when b is 2, my period is 180 degrees. Okay? When b is 3, what you would notice is that this point now happens at 120, 0. So that makes my period 120 degrees. And when b is 4, what you notice is that this actually happens at 90. So my period is 90 degrees. Okay, so what you notice is that as b gets larger, my period gets smaller. Okay? And moreover, what you might notice is that if I take the number of degrees in a full circle and divide it by this b value, you notice I get 180, which is the period. If I take the number of degrees in a circle and divide it by this b value, you notice I get 120, which is the period. If I take 360 and divide it by this b value, I get 90, which you notice is the period. Okay? So that's one main relation here, is that we know that the period is always equal to 360 degrees over b. If you're in radians mode, then it would be 2 pi over b, because 2 pi, of course, is the radian equivalent of 360 degrees. Okay? Alright. So now I want you to, I'm not going to spend as much time on these, but I want you to go ahead and graph them. So sine x, sine 1/2 x, sine 1/3 x, sine 1/4 x. So hopefully, once you graph those, pause the video, come back. What you'll notice is that instead of being compressed or pushed together like these are, these here are actually becoming elongated. So for sine 1/2 x, my period actually comes out to be 720. For sine 1/3 x, my period actually comes out to be 1080. And for sine 1/4 x, it's even longer. It actually comes out to be 1440. Okay? Which of course matches up with this formula here, because let's say my b value is 1/2. Then that means my p is equal to 360 over 1/2. So that would be 360 over 1 divided by 1 over 2, which to divide fractions I would multiply by the reciprocal. So 360 times 2 is 720, 1 times 1 is 1, so that gives me 720 degrees, which matches up with hopefully what you graphed in your graphic calculator. So the conclusion here is that my b value allows me to find my period. So my period is 360 over b, or 2 pi over b if we're looking at radians. Okay? Moving on to c. So what I want you to go ahead and do is graph these three functions here. Pause the video and come back. So hopefully what you saw is that when you graphed y equals sine x, of course it looks like that. However, when you graphed y equals x minus 90, you might have noticed something a little bit different happened. Is that this point right here, that was at 0, 0, is actually not there anymore. It's actually been moved over to 60, 0 when I graph y equals x minus 60. Okay? Alright? And then when I go to graph y equals sine x minus 90, what you hopefully see is that this point is moved over even farther now. It's actually moved over to 90, 0. Okay? So what I can see here is that x minus 60 took me right 60 degrees. X minus 90 took me right 90 degrees. Okay? Alright. So right 60, right 90 degrees. Alright, let's graph these three now. I think you'll see similar things happen, but you'll notice that instead of shifting to the right now, this thing here takes the original function and it shifts 60 degrees to the left. So this point that's at 0, 0 actually ends up right here at, I guess, negative 60, 0. Okay? And this one here actually ends up at negative 90, 0. Okay? So what you notice here is that this x plus 60 here shifts left 60 degrees. X plus 90 here shifts left 90 degrees. So the conclusion here is that if I have sine x minus some number, that tells me that I went right this many units, whatever this number is. If I have sine x plus this number, that tells me that I went left this many units. Okay? Alright, last one now, looking at D. So when I graph y equals sine x, y equals sine x plus 2, and y equals sine x plus 3, and y equals sine x minus 2. So go ahead, graph those, pause the video, we'll come back. Alright, so hopefully what you noticed is that when I graph y equals sine x, I still have the same shape that we've had before. So y equals sine x looks like this, of course. Alright. When I graph y equals sine x plus 2, well, just conceptually you can imagine that this is whatever I had with sine x, and I'm adding 2 onto it for its y value. So you know that whatever this y value right here is, it's got to be increased by 2. So instead of being, say, at 0.7 or whatever it is, it's now going to be at 2.7. So I think you can see then that everything that's here has to be moved up 2 units. Okay? Which should match up with what you graphed, right? So y equals sine x plus 2 actually started up here at 2 instead of at 0, 0. It actually started at 0, 2 and then took the sine wave, right? So really what happened is it was shifted up 2 units. Or in terms of the terminology used in the unit, you can see that my midline is now up here at y equals 2. Okay? So when I graph y equals sine x plus 3, the same kind of thing happens, except now it starts at 0, 3. So you can see then that my midline is at y equals 3. Okay? And even likewise, when I graph y equals sine x minus, what was it, 2? Same kind of deal happens, just instead of going up 2, it actually goes down 2. So at negative 2 here, my function starts, and you can see there's my midline at y equals negative 2. Okay? So my conclusion here is that D tells me the midline of the function. Okay? So moving on, we'll go through these quickly because I have 3.5 minutes. So this is an example that we started at the start of the session. So this is my A value. So if A is 3, that tells me my amplitude is equal to 3. My B value here is 2. So if B is 2, that means my period is 360 divided by B, which is 360 divided by 2, which is 180. Okay? I know to use degrees because of this thing here. It has 90 degrees on it, so that tells me to use 360 over B instead of 2 pi over B. My C value, well, x minus 90 tells me I moved right 90 degrees. The D is plus 4, so that tells me that midline is at y equals 4. Or it was shifted 4 units up. Okay? Next one here, so this is an example. You notice that because of this thing here, we're actually in radian mode. So I need to keep track of that when I do my period. But my A value is equal to 2 here, so this tells me that the amplitude is 2. My B, my B value is 1/4. So to find my period, remember I'm in radians, so I need to use 2 pi over B, which is 2 pi over 1/4, which I'll write as 2 pi over 1 divided by 1 over 4. Okay? To divide fractions, I multiply by the reciprocal. 2 pi times 4 is 8 pi. 1 times 1 is 1. So this is just 8 pi. Okay? So this B value of 1/4 gives me a period of 8 pi. C is in this case, well, the plus pi over 2 tells me that I've moved pi over 2 units to the left. Okay? It is pi over 2 because we're in radians, right? This D value here, this is meant to be a minus 1. So what this actually tells me is that my midline is at y equals negative 1, or it's just shifted down 1 unit. Okay? So hopefully that helps you understand sinusoidal functions.